In this video, we're going to close out Chapter 14 with titrations and titration curves. And so there's the learning outcomes and expectations. Feel free to pause. So yeah, section 14.7, acid-base titrations. Now, titration is just a general methodology to figure out something about an unknown solution. And so you can see the definition here. A solution of accurately known concentrations is gradually added to another solution of unknown concentrations until the chemical reaction between the two solutions is complete. And so this could be things like redox titrations or complexometric titrations. But for the sake of this chapter, we're talking about acid-base titrations. And so it's basically this idea if you're going to add a known acid to an unknown base or a known base to an unknown acid, and you're going to basically track the pH to learn something about the system. And so the way we're going to do that, or the common way to look at this information, is through an acid-base titration curve, which is basically a plot of pH versus the amount of titrant added. And so let's look at this experiment and what we're actually doing. And so what we do is we have some kind of unknown, something we want to learn something about. We will either want to identify the acid, the Ka of the acid, or the concentration of the acid. We put that in a solution with a known volume. In this case, we're going to call it 50 milliliters. And then we're going to take a known base. And so this is a solution that we've made. We know exactly the composition of it. We'll say it's NaOH, which is a common strong base, and we know the concentration of it. And so this is known. This is mostly unknown except for the volume of that solution. And so experimentally what you do is you measure the pH, add some base, measure the pH, graph pH versus volume, repeat that process over and over again. And so here's the graph of interest. So on the x-axis, we have volume of NaOH we're adding. That's the thing that we know about. We know the concentration of it. And then we're going to measure pH. And so we stick a pH probe in this solution. We can measure the pH of the solution. And so let's say we measure the pH of the starting solution, and it gives us a pH of 3. So what's going to happen when we add base to it? We add this NaOH, we're adding OH minus to this solution. So we know it's an acid because the pH is below 7. It's pH 3 starting. It's an acid of some kind. We'll call it HA. We're going to add OH minus. It's going to turn that OH, that's going to deprotonate that HA and generate the conjugate A minus as well as H2O. And so let's add a drop of OH. Let's measure the pH again. We get another data point. We add more OH, it's going further and further this way. Measure the pH. You can see the pH goes up with each addition. We're going to do this again. We can repeat this process over and over, right? Add drops, add pH, and we're going to see, okay, pH is going up. We see a really sharp increase in the pH, and eventually we see the pH plateau at, in this case, it's somewhere 13 or 14. And so we've effectively started out with an acidic solution. We're adding OH minus, converting some of that HA into A minus, and we can see the pH of that solution going up. And so if we did this as a continuous line or collected a whole lot of data points, it looks something like this. And this is what we mean when we say acid-base titration curve. And it turns out there's a lot of information in this curve. This is a very information-rich outcome of that experiment. And so the first thing we'll talk about is the equivalence point. And so you can see the definition here, point in a titration at which the amount of titrant added is just enough to completely neutralize the analyte solution. What does that mean? So we've done this reaction, we're taking HA, which is our starting solution, we're adding OH minus, and it's eventually increasing, and then we see it do a sharp increase. And so what we're doing is we're converting HA to A minus. Well, what happens at this equivalent point is effectively we added enough moles of this OH minus that we've converted all the HA to A minus. And so effectively, if we know this equivalence point here, this really sharp incline, that's the threshold where the amount of OH minus has been equal to the amount of HA. And because we know the initial concentration of NaOH, we know exactly the concentration of HA. And so let's just look back at these numbers. So we started with 50 milliliters of an unknown. We don't know what the concentration of this is, but we do know the concentration of this. We know it's 0.1 molar. And so we can find the unknown concentration here based on the NaOH amount we added, because at this point, we know that those amounts are equal. And so here's our knowns, 0.1 molar sodium hydroxide or 0.1 molar OH minus. That's our stock solution here. We know what the volume of this solution is. And so if we look at our graph, we saw, okay, we needed to add 25 milliliters of NaOH in order to neutralize. That's what this upward curve, this sharp incline means. It basically means at this threshold, OH minus is 1, and it's just OH minus and A minus from there. And before that, there's some HA and A minus mixed together. OH minus wins right here, and it takes over, and that's why the pH increases so much. And so we needed 25 milliliters of OH minus to tie the concentration of HA, and any more addition beyond that, OH minus wins. And so at the equivalence point, we know we needed 25 milliliters of NaOH. And so we know we started with a 0.1 molar per liter solution. We added 0.025 liters, or 25 milliliters. And so it means the amount of OH we had to add to reach that point is 0.0025 moles. That's how much moles of NaOH we added. And so because we know at the equivalence point the moles of OH minus equals the moles of HA, it means the amount of moles of HA in this solution was 0.025 moles of HA. And since we know the volume of that initial solution, the original concentration of HA was 0.05 molar. And so just to recap, we started with a volume of unknown concentration. We started with a concentration that's known. We added enough of the NaOH to reach the equivalence point, which is this really sharp upward incline. It's the point basically in the middle of that upward incline. We know how much NaOH we added. We know what our starting concentration was, so we figure out the moles of OH minus. If we know the moles of OH minus, it turns out we know the moles of HA, because at the equivalence point, those two are equal. And since we know the moles of HA and we know the initial volume of HA, we divide that calculated mole by the initial volume, 0.05 liters, and we get a 0.05 mole solution. And so effectively, yeah, that equivalence point, if you know the volume added and you know the concentration, it tells you how much of the acid. And so it doesn't tell you the identity of the acid, it only tells you how much of HA was present in that solution. The other thing we want to know about it is the midpoint, or the half equivalence point. Basically, it took us 25 milliliters. At that half point, 12.5 milliliters, we reached a very specific threshold in this acid-base titration curve. And so remember, at the equivalence point, when we get to this blue dot, we've said the amount of NaOH we added is equal to the amount of HA we started with. And so we've neutralized all the HA. Well, what happens at that half point? Well, at the half point, you're only consuming half of the HA, which means basically you have a 50-50 mixture of A minus and HA. And so this point right here, this halfway, so you go here, it's 25 milliliters, halfway to that is 12.5. That's the halfway point. That's the threshold where HA is equal to A minus. And so if you remember back to the Henderson-Hasselbalch equation from our previous PowerPoint, when HA equals A minus, this becomes 0, which means pH equals pKa. And that's really important on this graph because effectively that goes away. The 12.5, you go up to the line, that pH, whatever pH that midpoint or half equivalence point is, that is the pKa of your acid. And so effectively the shape of the curve intrinsic to it, you have an equivalence point where they're equal. You have a halfway point where HA equals A minus. At that halfway point, draw it over to the x-axis. That tells you the Ka of the acid. And so from the equivalence point, we got concentration. From the halfway to the equivalence point, we got the Ka of our acid. So that tells us something about the strength of the acid. It doesn't tell us what the acid is necessarily, but it narrows down the possibility based on that Ka value. The other thing we have from this graph that's important is we have a buffer region. Again, we talked about that previously. A buffer region is basically where you have this plateau, this semi-unchanging pH. That's exactly what we're seeing in this graph. So you see a quick incline, and then you see it largely plateaus, and then it does have another quick increase in pH. And so this region right here, it's acting as a buffer. And so if you have a 50-50 mixture of HA and A minus, you add some acid, it's going to go this way. You add some base, it's going to go this way, but it's not going to change that much. And so we talked about buffer capacity. How good is it at resisting it? How long does it stay plateaued? We also talked about, the buffer region. We want to stay within plus or minus of this. That's what this buffer effectively does. It's resisting change this way. It's resisting change this way. And so we see the buffer region on this titration graph. Not only that, but the shape of the titration curve tells you something about the nature of the acid and the base. And so it tells you whether it's an acid or base. It tells you whether it's strong or weak. It also tells you whether it's mono or polyprotic. And so this curve right here, it turns out this is adding so you're always going to add a strong acid or a strong base to whatever your unknown is. That's just the nature of the problem, at least under normal conditions. And so this shape of this curve tells you something about the acid you're starting with. And so the shape of this curve actually represents a weak acid, and you're adding a strong base to it. The reason we know it's a weak acid is it's not starting at, it's an acid because it's below pH 7, right? But it has this S-curve shape, and that S-curve basically says there's a buffer region here. It basically tells you it has to be a weak acid and a conjugate base. Also, the equivalence point is greater than pH 7, which means you're generating A-, which is a basic species, which is why the equivalence point is there. And so even if you consume all the HA, you still have a bunch of A- laying around, so it's not a neutral solution. The pH is actually above 7 at the equivalence point. Now, if you tried to titrate an unknown and that unknown was a strong acid, you're going to get a curve that looks more like this. Strong acids don't really have a buffer region. I mean, they plateau, but they don't have like that S-curve shape with them. Also, the pH, you can see it starts at 1. That's typically only going to happen if you have a strong acid. The other thing that gives away that this is a strong acid as you're starting is when you combine a strong acid and a strong base, you're going to reach an equivalence point at pH 7. And the reason that occurs is because you started out with a solution of H+, you're adding OH- at the equivalence point. Both of these are equal, which means all you're generating is H2O, and the pH of pure H2O is 7. And so that tells you that this is a strong acid. You can do the inverse, right? You can take a unknown base and you can add a strong acid to it. And so your curve is going to look something like this. You're starting with a high pH. You add acid, it's going to have a buffer region. It's going to go down. It has an equivalence point. All the same rules apply. It's just in this case, you're using a base as this. You're adding an acid to an unknown base. And so, again, it starts above pH 7 but below 14 because it's a weak base. It has that S-curve shape. It has an equivalence point below pH 7, and it's for the same reason that this one had a pH above. Basically, you start out with nothing but A-. You're generating HA. All A- is converted to HA. At the equivalence point, you have extra HA, which gives you a pH that's less than 7. And so, yeah, you can tell by looking at the graph. Is it a weak acid? Is it a strong acid? Is it adding an acid to a weak base? Similarly, you could add a acid to a strong base, which would basically be flipping this graph over. The other thing you can tell if something is mono or polyprotic. And so let's take an example with H2SO3, and we're going to add sodium hydroxide to it. And so looking at this molecule, we'd already say, okay, this is a diprotic species. It's going to lose one proton. That's going to be a conjugate base, but also an acid. It can lose a second proton. And so it turns out here's what it looks like on the curve. And so you can think about each part of this curve as being exactly the same as the ones we just showed. You start out with this, you add base, it's converting, you'll have a 1-to-1 ratio of these two, you'll reach an equivalence point where all this is converted to this. But this one keeps going because we can add more NaOH, and it's going to convert some of this to this. You get another buffer region, another, in this case, it's a half equivalence point or halfway between this equivalence point and this equivalence point. That's going to be the second deprotonation event, and then you're going to have a second equivalence point. And so this shape tells you a lot about the system, right? It effectively, because you see two of those S curves, it's a diprotic acid. If you saw 3, it's triprotic. If you only see 1, then it's monoprotic, or you haven't gone far enough to see the subsequent ones. But you see 2 buffer regions, you see 2 equivalence points, you see 2 half equivalence points. It's basically you have an acid making the conjugate base. The conjugate base behaves as an acid, and then eventually you have the conjugate base that can't be deprotonated anymore, and you get a really high pH in that case. And so same rules apply for the most part. You use the first equivalent point to figure out concentration. You could use the second, but you'd have to divide by 2 because there's 2 protons generated. You have a buffer region, you have halfway to this first equivalence point, that's your pKa. Halfway between your first and second equivalence point, that's your pKa for the second step. And it's basically because half of this was converted to this. At that point, pH equals pKa. That's your pKa value for the second step of that process. And so, yeah, tells you the number of protons, tells you the concentration, tells you the Ka1 and Ka2 of this process, tells you what the buffer regions are. You can mix these two and make one buffer. You can mix these two and make another buffer, and it shows you where those would be effective buffer regions. So just a quick summary on the acid-base titration curve. Here's our graph for a weak acid being titrated with a strong base. We have the equivalence point, tells us when the amount of base equals to the initial amount of acid. We have a half equivalence point, or a midpoint, where it's halfway to the equivalence point. It tells you the pKa of the acid. We also see a buffer region. Not only that, we can look at the shape and we can know acid versus base, strong versus weak, monoprotic versus polyprotic. So yeah, a lot of information. But what if you don't have a pH meter and you don't get pretty graphs like this and you still want to know the concentration? That's where pH indicators come from. And so all a pH indicator comes from is basically a color change that's associated with pH. So you have some species, we're going to say IN, shorthand for indicator, and that IN is going to donate an H plus and make the conjugate base, and that's going to have a different color. And so it basically says the acid and the base form have different colors, and so we can use that color change to figure out what the what the pKa of that acid is, or what the equivalence point is. And so going back to Le Chatelier's principle, this idea, if you add acid, it's going to shift this way. It'll be this color. If you add base, or effectively remove H plus by adding OH minus, it's going to shift this direction and become this color. And so we're going to rely on this shift in equilibrium related to this indicator species to effectively tell us, roughly what the pH of the solution is, or what the pH of the equivalence point is. And so here's just an example of a real molecule that does this. It's basically two different forms. This one is the basic form. This is the acidic form. If the pH is less than the pKa for this proton right here, then basically the solution is more acidic. The solution wins. It donates its proton to this guy. If, on the other hand, the pH is greater than the pKa, this tells you the surrounding environment is more basic than the molecule is, and so it's going to steal that proton away and be this form. And that's effectively what these indicators do. They have some kind of structure that has a pKa associated with them, and that structural difference gives you a color change. This guy is red, this guy is yellow. And so we can utilize what's a known reference to tell us when that threshold is being crossed. And so when you're doing a titration and you don't have a pH meter, the thing you look for is effectively that color change, right? And so if you're doing phenolphthalein, which is a molecule that looks like this, it goes from colorless to pink as soon as you cross a threshold from pH 9.2. And so below 9.2, it's going to be colorless. Above 9.2, it's going to have a pink or a purple color associated with it. And so we can use phenolphthalein as this reference to tell us, are we near that 9.2 mark? As soon as we cross that 9.2, we're going to get a color change. And that's exactly what happens. So going back to our titration curve, if you have a phenolphthalein indicator in your solution, it basically says below, anytime this line is below a pH of 9.2, it's going to be colorless. As soon as it gets to that 9.2 threshold, or close to that 9.2 threshold, it's going to start to change color, and it's going to turn into that pink red color. In fact, this coloration line should extend up to the top because it'll stay that color. And so it'll be colorless, 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 reaches a threshold of pH, and all of a sudden it becomes a color solution. And so if you see that color change and it's on this upward inflection, that effectively tells you where the equivalence point is. And so even if you don't have this graph, if you saw that color change happen really quickly and you know exactly the amount you added, that is because it reached this equivalence point, this really sharp increase in pH, and you get a really dramatic color change fairly quickly with low changes in concentration. And so when choosing a pH indicator, you kind of have to know where your roughly what pH your transition is going to occur. And so you kind of have to know where that transition is going to be. And so if it's going to be in a range between pH 3 and pH 11, you want an indicator that changes color in that range. So here's an example with phenolphthalein and methyl red. If you use thymol blue, and you can see the pH range or the pKa, rough pKa values of these, thymol blue will change color basically from the start. But you want ones that are going to change on this upward inflection. And so if you know roughly where it's going to be, usually it's going to be somewhere pH 7 plus or minus 2. You pick an indicator accordingly so that the color change happens on that upward curve. And so unfortunately, you do need to know something about your acid before doing this process, whereas if you're going to generate the pH curve, you just start from scratch and you can make it from there. All right, so there's a summary. An acid-base titration curve, we have a plot of the pH versus the amount of titrant added. You know the titrant, you measure the pH, and so through that you get a lot of information. It's an information-dense graph. It tells you the concentration from the equivalence point, the strength of the acid from the shape, as well as the half-equivalence point or the Ka value. It tells you what the buffer region is when you see it plateau versus sharp increases. It tells you where it'd work as a buffer. The number of those inflections tells you the mono versus polyprotic, as well as the number of equivalent points. And even if you don't have a pH meter and can't do titration curves, you can still figure out concentrations based on pH indicators, these things that basically change colors when there's a change in pH. And if that change in pH is on that upward curve, that color change corresponds to the equivalence point. So if you know that equivalence point, you get the concentration. Unfortunately, it doesn't tell you things like pKa and buffer region, but you can extrapolate from that equivalence point some of that information. So yeah, that tells you about titration curves. That also closes out our discussion on acid-base equilibria. So chapter 13, we introduced the general idea of equilibria. In chapter 14, we dove into this, very specific subset of equilibria, which is related to acids and bases, or gaining and losing a proton. So we introduced things like Kw, Kas, Kbs, pKs, pHs of solution, pOHs, and related all those variables together. And then we talked about buffers, which is trying to negate the effect of pH change, and finally close with acid-base titrations, where we can actually learn about these species, both the concentration as well as the Ka values and the buffer regions. So yeah, next we'll dive into chapter 15, which is a few different versions of equilibria.